Good afternoon and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager at Burns Engineering, and presenting today will be Bill Berquist, Senior Applications Engineer. Today's presentation, Improving Temperature Measurement Accuracy in Biopharmaceutical Processes, is part of our continuing series of web-based training modules designed to help you better understand temperature and achieve your measurement goals. If you've joined us for our previous sessions, we'd like to welcome you back. If this is your first time with us, welcome. And when you get a chance, do go ahead and check out our previous presentations on the RTDology page at burnsengineering.com. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We highly encourage questions, so please type them into the Q&A section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. Today's session is being recorded, and we will provide session notes and a link to the recording to all participants as soon as they are available, so don't worry if you miss something. If we don't get to your question or you need some additional assistance, there will be contact information provided at the end of the presentation. And finally, our goal is to answer your temperature measurement questions and challenges. We've built RTDology around commonly asked questions and issues. However, if you have a particular topic you'd like to have considered, do give us a call and we'll customize a presentation for your needs. That covers the housekeeping, so without further delay, here is Bill Berquist to share some insights on improving temperature measurement accuracy in biopharmaceutical processes.
Well, good afternoon, everybody. Today what I want to do is talk specifically about how to improve temperature measurement accuracy, and we're specifically going to look at how we select the temperature probe and then some of the things we can do for the installation. Some of these errors that are associated with measuring temperature with an RTD, the bigger inaccuracies are usually related to the installation, so we'll probably spend most of the time on that particular section. But first I want to start out and talk about the sensor selection. We'll go through some of the specifications that you need to look for when selecting an RTD. First off, all RTDs are not created equal. We have, there's a whole variety of quality and performance levels with RTDs. There are a couple of specifications or standards that control some of the performance parameters, and the first one of those that I want to look at is the sensor interchangeability. And if we look at, trying to define what this is, if we've got a bundle of sensors and we pull one out of that group, what it says is that it's going to fall within a certain kind of closeness of agreement with a specified or predefined R versus T relationship. The two current standards that are out there, there's an ASTM standard and an international standard. And there are some equations that define what the interchangeability tolerance is at any given temperature. So if we, for example, if we were to look at the first one on top here, the ASTM standard, what we call a grade A tolerance, you plug your temperature in degrees C into this equation and run the numbers, and it'll give you what that interchangeability number is. If we look at a comparison between the two standards, we can see that the IEC standard has a little wider tolerance range than what the ASTM standard has, and both have either a grade or what we call a class A or B. And in the IEC standard, there's a couple more being added. There's a class AA and a class C. So this is kind of that's one of the first things you want to look for is, okay, which one of those do you want to select for your process? The next thing to look at in the performance specs would be the long-term stability or the drift rate of the part. And this can vary quite a bit between the different sensor designs. It varies a lot between manufacturers also. This is a kind of a typical range of drift that you would see with a typical industrial quality RTD. And for most of the biopharm processes, we're going to be running under 200 degrees C. So you can see that it's going to be 0.0 something degrees C. Generally, this is kind of a worst case scenario here. So the actual typical numbers that you'd see in a process would be roughly half of what you see on this graph. So if we run a RTD at 200 degrees C for 1,000 hours, we can pick a number off of this chart. Looks like it might be 0.05 C, for example. Most often you're going to see about half that. So drift under 200 C is usually a pretty small number, but it is something that you would need to include in your error budget calculations. The next thing to look at, well, let me back up here. Those are two of the more important specifications to look at. But when we're trying to move beyond that plus or minus half a degree C accuracy range, you really need to look for a manufacturer that publishes a whole bunch of other performance characteristics, and we're going to look at some of those later. But there are other things in addition to the interchangeability and the drift. There's temperature cycling, hysteresis, vibration resistance, and those are just a few of the things that you need to concern yourself with when you're calculating an error budget for a particular measurement point. The next thing to look at when selecting an RTD would be the type of electrical connection to it. We have 2, 3, and 4 wire circuits that can be used with RTDs. The most common are the 3 and the 4 wire. And when we're looking at providing a high accuracy measurement, the 4 wire is the one that wins out over all the others. So the other part in a RTD, there can be kind of a thermocouple effect or an EMF created, which is caused by internal junctions within the RTD. You're joining dissimilar metals in some cases. And again, this varies by manufacturer. There are ways to minimize it, but without the proper precautions there, you can have a measurement error caused by EMF within the probe. So, how can we get rid of those? Well, the 3-wire connection, this relies on all 3 of the leads having an equal resistance, because your control equipment is going to assume that the compensation loop, typically there's 2 red leads and 1 white one. And it'll measure the 2 red leads and then subtract what it sees there from the white and 1 of the reds. And in the real world, all 3 of those leads don't necessarily have exactly the same resistance. And if we look at a typical 18 gauge cable, a worst case scenario, we can have about 0.16 Fahrenheit for every 100 feet of that cable. And if we look at some other kind of typical numbers here that we've calculated for the different wire sizes, let's say we've got a grade A sensor and we've got 22 gauge leads. We can typically put about 15 feet of lead wire on that sensor and still have that sensor maintain its original interchangeability tolerance. If you go over that, there's a good chance that you're going to fall out of that tolerance range. The sensing element itself is still going to be within, but where it matters is at the end of that cable, and that's where you need to concern yourself with the length of the cable and the wire size that it's attached to. Now there are ways to eliminate this by balancing the lead wires. So you would take all 3 of those leads and measure them, and then adjust the low ones up so that they all have roughly the same resistance.
So, Bill, can you talk just a little bit more about that lead wire balancing? Because that's typically something that's done by the manufacturer, not necessarily something that would be done by the end user, correct?
Right. That's the best way. I mean, they typically would have the right equipment to be able to do that. You may see things like, you know, the cable may be labeled with, you know, do not cut cable or accuracy will be affected. And, you know, typically what's happening there is that they've put some kind of a trim resistor in that cable, right, typically at the end of the cable where, you know, where you can get at it, you know, to make the adjustment. So if you do have a sensor that has a long extension cable on it, you know, look for a label like that. And if they're, you know, if you've got, you know, 30 feet of cable, 22 gauge cable on an RTD, and there's no label and there's no anything that says that it was ever balanced, that should maybe raise a red flag, and you check that just to make sure that it's, you know, it still falls within the tolerance that you're expecting it to be at. The easiest way to get rid of all that is just to use a 4-wire circuit. They fully compensate for the lead resistance, and then if you have a bad terminal block, or if you have a connector where you're connecting an extension cable, that fully compensates for any variance in resistance between each of those 4 conductors. So this is really the best way, and it's especially the best way if you have a long extension cable from the RTD back to your, you know, like any kind of signal conditioning equipment, whether it's a chart recorder or PLC or whatever it might be.
So, Bill, just one more comment on that 4-wire. As far as recommending that, you do have to have a control system or transmitter that handles a 4-wire system. Otherwise, you don't really get the. A lot of times, we will see people that go ahead and buy a 4-wire, and then they only connect it up to 3 terminals. You don't get the benefit if you're not able to connect it up correctly with the control system or the transmitter that you have.
Right. In years past, I think the state of the art with the electronics and transmitters and things said 3-wire, and now most of the even some of the smaller little hockey puck transmitters and things, they all have a 4-wire input. You do need to make sure that it is a true 4-wire connection and not just a you know, that they're putting a jumper between a couple of the terminals to make it look like it's a 4-wire. It does have to actually do the full current potential lead wire compensation. You know, so if we look real quick here at some electrical diagrams, you know, with a 2-wire sensor, you're just adding lead resistance into the sensing element, and you're going to get a, you know, too high of a temperature reading. So it's really not recommended for anything to do with any of the biopharm processes. 3-wire, this works okay if you have like a you know, a sensor that's going right into a terminal block inside of a connection head. You may have a transmitter there, so you've got very short lead wire run. There really wouldn't need the 4-wire, although it's still it would be good practice to do it, but 3 wires work just fine in those cases. And the 4-wire connections or current potential method shows how it fully compensates for any resistance that you have in the wires coming from the sensing element. Another way to look at this, for every 0.04 ohms of variation between each of the 3 leads in a 3-wire, you end up with about a 1/10 of a degree C error. And the smaller the gauge wire, the worse that error gets. And of course, if you use bigger wire, it gets smaller. Next up, I want to talk a little bit about the one of the bigger kind of installation errors that we see, which results from insufficient immersion of the sensor in the process. A lot of the biopharm processes use, you know, 1/2-inch tubing, you know, maybe on up to 2 or 3 inch at most, and there's always it's always a big challenge to figure out what is the best sensor design to fit in that kind of a process. You know, how far does it need to be immersed, and there's a balance there between the immersion length and the flow rate, because one of the things that is done to minimize this what we call either a conduction error or immersion error is to use a small diameter sensor. And when we do that, there's a balance there between the strength of the sensor and having it perform well enough to overcome this conduction error. And if we look at a rule of thumb for a direct immersion sensor, we like to have 10 times the probe diameter plus the sensitive length of the sensor, which is typically about 1 inch. And then if we look at a 1/4 inch diameter sensor, 10 times that is 2.5 inches plus that 1 inch sensitive length. Says we need about 3.5 inches of immersion. And if you have a 1/2 inch line or a 1 inch line, that becomes a bit of a challenge. You need to install it in a T fitting or do some other things to be able to do that. And we're going to look at what those are. What's happening with this conduction error is that we have a process. This one's running at 200 degrees C, and we got 25 C ambient. So we have a differential there of temperature, and so you're going to actually have some cooling effect on that sensing element in this process if you have insufficient immersion to overcome it. And the reverse of that works also, if you have a cold process and a warm ambient conditions. And then the best case is if your fluid process is running at ambient conditions, well, there isn't going to be any conduction error noticeable in that situation. So to look at some of the probe types to overcome this, one of the first things to look at, we typically have 2 options here. We can do a surface mount sensor, and for improving anything beyond 0.5 degrees C accuracy, pretty much avoid those. It's going to be very unlikely that you're going to get anything better than 0.5 degree C with something like that. The best way is to go with an immersion, whether it's direct or indirect, which would be a probe inside of a thermal well. Some of the sensor designs that work well, and this is what we call a mini sanitary. It's an 1/8 inch diameter stem, typically has a 1/2 inch or maybe even 1.5 inch sanitary clamp fitting on it. And minimum immersion on something like this is about 1.1 inches. It can be installed into the outlet of a T or the run of a T, and works fairly well for steam or liquids. Another variation of this one is it's a similar design, but this one has a separable thermal well, so you can leave the process sealed up. It's a 3/16 diameter removable sensor, and 1.25 inch immersion is about the minimum that you'd want to do with something like this. There's one exception to the surface mount, and this is a bit of a hybrid that is a sensor that's bonded to the tubing, and then there's a stainless shell welded around it and insulated heavily. Typically what you'll see with this is that it's not going to measure the exact fluid of the temperature, but the measurement is fairly repeatable, so that if you can make some adjustments in your measurement loop to compensate for it, it will give you a fairly repeatable number. And this would really only be used where you have really viscous fluids or stuff that would accumulate around an immersed sensor and build up. So it's kind of a limited usability for high accuracy measurements, but it is an option where an immersion style sensor cannot be used.
So just a quick reminder to everybody, if you do have a question or a comment, do go ahead and type that into the chat box or the Q&A section and send it to host and presenter, and we'll try to get you an answer to that question. We don't actually have the phone lines open because we found it gets a little chaotic with so many folks on a presentation with open phone lines. So if you could just type it into the chat box or the Q&A section, we would greatly appreciate it.
Yeah, I'd also like to add to that too. If anybody has any, comments on things that they'd like to see in addition to what we're showing here, or if there's, if in your experience you've learned anything else about this kind of thing, I'd sure like to hear about it too, and you could plug that into the chat box and we could share it with everybody else.
Right. Just to kind of tag on to that, Bill, the reason we actually put together this presentation is because we have been getting several requests over the last, I want to say maybe 4 to 6 months for folks looking, particularly in the biotech, biopharma world, looking to get beyond what has traditionally been the threshold of ½ degree C accuracy. Really looking at ways to get beyond that, and so we certainly, it appeared that there was a need, and so we wanted to you know, let folks know what was possible. And you know, one of the things that we're always looking for is more feedback as to what challenges you out in the industry are facing and how we might be able to help you meet those challenges. So as Bill said, if you do have comments, by all means go ahead and type them in as well. We would greatly appreciate it. Okay, thanks, Jeff. So this assembly here is one of my favorite ways to overcome this immersion problem in small diameter lines, and it's you know, it's called elbow thermal well, or it goes by a few other names too, but anywhere from, you know, ½ to 4 inch lines we can do something like this in. And there's a small thermal well inside of this device. We got a little cutaway that shows how this is set up. One of the other benefits of this style, we can get enough immersion length, and let me go back here. You can see right where the tubing is flared out here, and that's so that there's no, we're not restricting the flow as it's going through this. And the thermal well portion rests inside here, and it can use a standard removable sensor, whether it's you know, tip sensitive or just a standard sensor. And we can get enough immersion length to overcome the stem conduction, and having the fluid come directly at the tip of the sensor, like we show on the diagram here, maximizes the strength characteristics of that particular thermal well. So it can be used in higher flow rate applications than a sensor that may be installed you know, at right angles to the flow, for example. Some of these other applications that do have you know, high flow rate and they need the extra strength, there's typically, like this, would be heavy duty, where it's a ½ inch diameter probe and it steps down to either a 1/4 inch or even an 1/8 inch diameter sensor. This particular one's a 3.5 second time response. Another variation on this is with a removable well. This happens to be 3/8 diameter. Attaches, in this case, with a tri-clamp connection. And then for those applications where we need super fast time response, you know, you may have a process that changes quickly, a direct immersion sensor. This happens to be about 83 thousandths diameter, and it's actually welded right into the tubing. So if you were to look inside this little sanitary elbow, you'd see the sensor inside, and it's about, oh, maybe a 1 inch immersion roughly, and works fairly well as long as the, you know, the flow rate or the viscosity isn't too high to damage the sensor. So that's a few different ways of getting around this immersion length issue with kind of a variety of different sensors that you can look for. Hey, before we move on, just we've got a few questions and comments here that before we get too far, I think we should probably address. A couple points from Joseph talking about surface mount as being a great alternative to strapping a round RTD to a round pipe, which I think is along the lines of, if you've got something designed specifically for your application, you're going to get a much better measurement than trying to use something that's a little bit more catalog, if you will. Also, a comment about using heat transfer paste or silicone liquid to eliminate the air gap. Can you talk a little bit about that, Bill?
Right. Yeah, this is a question I do get quite a bit, and some of the concern there with this, like if we look at something like this where we can use a heat transfer paste in this type of a RTD thermal well assembly. One of the concerns is that, especially with biopharm processes, that we're introducing another material into this process, and if something should break internally, you have that material getting inside of your system, and it could be a real big problem to clean it out of there. Whereas if you just have, stainless parts and something goes to heck on you, that's a little, it's still a problem, but it's not as big as if we have some, kind of semi-unknown heat transfer paste that you got to start cleaning out of the whole system. It does make a big difference in time response, and it does eliminate any air gap between that probe and the thermal well. So you do get a lot better heat transfer characteristics. And if there's a situation where you needed the time response improvement, that can really make a big difference. One of the other ways to do this without the heat transfer paste is to use a sensor that has a small copper tip on it, so it has a little better heat transfer as it's bottomed out right against the bottom of the well. Stainless is actually a very poor conductor of heat, so that having that copper tip on the probe and the sensing element we potted inside of that, that can be another potential solution there. I've actually got a chart later on here that shows the difference between those types of installation with the heat transfer, the tip sensitive, and then like a standard direct immersion sensor. And we'll get into that in this installation thing. But it looks like we got some more questions.
Yeah, one more question had to do with the elbow well. And does an elbow well increase flow resistance significantly?
The tubing is flared out around the thermal well portion of it, so that the objective there was to not restrict the flow at all. The actual cross section of the tubing that's available for the flow does not change when it gets to that sensor. So typically we really wouldn't see any flow restriction there.
Okay, another question, is there any data for the size of bleeders if immersion cannot be 3.5 inches or 10 times the diameter?
I'm not sure I quite fully understand that question, but
I think maybe you want to talk a little bit about the if you go down in diameter with the sensor, you don't need to go quite as deep with immersion.
Well, I guess if we look at what we've seen with like that 1/8-inch diameter mini sanitary, the first one we looked at, it's 1/8-inch diameter, and we get by with about 1.1 inches of immersion. And there where it uses a sensing element that only has a sensitive length of it's just probably just over 1/8 of an inch, and the tubing is 0.125. So if you were to use our rule of thumb, it says, well, it should be about an 1 1/8 of immersion, maybe a little bit more than that. But we've had enough field experience with that to know that it works really well down to that 1.1. More immersion is always better, but again, you need to weigh that against the effects of the flow rate on the sensor.
Yeah, I think the key here is if you've got a specific application that you've got a concern about, I think the best way to address that would be just to shoot us an email or give us a call and lay out the specifics, and then we'd be able to give you a much better idea of what's possible and what the concerns are.
Okay, is that it for now?
Yeah,
then?
I think that's it for now. You can continue on. There's a couple other questions, and we'll go ahead and catch those up more towards the end.
Okay. So the next part here, I wanted to talk about installation. This is where we see some of the biggest errors, and just wanted to show a few different ways. I'd mentioned this already with putting a sensor in a T-fitting. Again, that elbow thermal well, the big advantage of that is it eliminates, any kind of dead lag here, because it trims off the T-fitting rate in this location. This does work fairly well, though, as long as you have the flow rate coming directly at the tip of the sensor. So this is one way you can do it. If we look at some of the other ways, you can have the, things don't always work out, but the flow could be coming in from this direction, although you do leave some dead space there. Worst case is to put it in the outlet like this, and again, the best is this having the flow come directly at the tip of the sensor. This is a chart I'd mentioned where we have, if we can look at this shows the conduction error or immersion error, and it's expressed as a percentage of the delta T, or the difference in temperature between ambient and the fluid temperature. And if we have a tip-sensitive probe in a thermal well, we're down here at near zero. The next, and these are almost identical here, where it's just a standard RTD in a well. Just a slight difference in accuracy between those two. Tip sensitive is a little better. It's got a little faster response, and of course the direct immersion sensor right here does a very good job. Now you can see that the non-intrusive sensor, we can get up to about just over 2% of that delta T number as an error. So that, again, it works fairly well. It's fairly repeatable. Our kind of worst case here, again, it's the surface mount, no heat transfer paste between the sensor and the tubing, and no insulation over the top of it. So it gives you really actually pretty poor representation of the fluid temperature inside the tubing. And this shows just the effect of having air blowing on the sensor. We had a situation once where there was a measurement error, and we were trying to figure out what it was, and we eventually figured it out that there was a fan that was blowing in the factory, and it was blowing on the sensor, causing a pretty significant error in that measurement. Redirect the fan, the error went away, and problem solved with that one. So you can see here that, again, the surface sensor being most susceptible to additional air just with airflow going over it. And the best case here is a tip-sensitive sensor. And it could be, these are typically used in a thermal well because they do have a copper tip on them. So this shows another potential error source for this. And when we talk about immersion length and a trade-off between the immersion and the strength of the part, if we were to look at just a 1/4 inch diameter sensor, an acceptable flow rate is down here about 30, maybe 40 feet per second. We add a big thermal well to it, and that goes up to about 250. What's happening here is that when you have a sensor installed in a flow rate, there are some turbulence that can form just downstream of it, and they can actually cause as soon as the frequency of that oscillating turbulence downstream of the sensor matches the resonant frequency of the probe, it can start to vibrate, and it will destroy the element, and worst case, it's going to break off. So you need to balance that immersion length against the strength and wake frequency specifications for that part. Another chart here shows how the immersion of the probe influences the air, and this happens to be just for kind of a larger industrial style sensor and thermal well setup. It's going to be very similar though for other smaller diameter sensors, where we come down and we look, the immersion air starts to disappear just over 2 inches of immersion, and by the time we get up to 4 inches, maybe 4.5, it's nearly gone. And this was a test that was performed in an ice bath and also 100 degrees C oil and 200 degrees C oil bath. So it's fairly immune to the differences or the temperatures that it's in. It's just, it shows just the effect of kind of shows the magnitude of the air with when you have insufficient immersion. Now, one of the easiest ways to go ahead and improve measurement accuracy is to match the RTD to a transmitter. Now, there are other ways to tune the whole measurement loop. You know, you may have other instruments in there, or it's doing other things. And I'm not going to get into talking about that today. What I can do is talk about how we can take a temperature sensor and a transmitter and actually match those together, whether we're doing a transmitter that has the capability of having temperature coefficients and the R0 numbers plugged into it, or if it's an analog transmitter where you just have zero and span adjustments. You can go ahead and adjust those so that you're matching that performance characteristics of the RTD to the transmitter at those two places. Some of the programmable ones, we can plug in the coefficients so that it generates that R versus T curve in its brains and gives you the best accuracy throughout the whole range. And some of the equipment that is needed to do the matching might be a decade box, so you can plug in the resistance of the sensor and use that along with an ammeter and a high accuracy, high accuracy voltmeter and ammeter power supply. That way you can go ahead and set it up. Others, again, may use a software package to do the programming, and the RTD manufacturer or your own lab can calibrate that sensor, generate the coefficients, and match it up that way. And when we look at a comparison of just taking a grade B sensor, grade A, and then doing a match, you can see quite a dramatic difference in accuracy here. And we just combined the error sources using root sum square. So we've got 0.77, and that improves all the way up to 0.11 degrees C for that matched RTD and sensor. In addition to doing the matching, to go ahead and maintain that accuracy over time, we really need to go back and check that RTD periodically to make sure that it hasn't drifted or something else hasn't happened to it. You can also check that matching with the transmitter. Two of the simplest and most important checks to do is insulation resistance, and then to measure the ice bath resistance. RTDs can pick up moisture inside if the moisture seal where the leads are coming out has failed, or if it's a very old sensor, sometimes moisture can get in over a long period of time. And you're going to see a drop in the measured temperature. And what's happening, moisture gets in and acts as a shunt between the coils on the platinum wire or on the lead wires, and it's going to drop the resistance. Electricity takes the path of least resistance, and it's not always through the platinum wire or any of the lead wires. It might be jumping between them because of the moisture that's in there. You test that with an ohm meter, and at room temperature, you should have at least 100 megohms at room temp. Test is 50 volts DC. This is probably the lowest level that you'd want to test it at. There are manufacturers that may go up to 500 volts and maybe 500 megs or even 1,000 megohms. the only reason for that, for the high levels at room temp, is that as you go up in temperature with that sensor, the insulating capabilities of the materials decreases. So you want to make sure that it's high enough at room temperature so that it's going to be okay at the higher temperatures.
So Bill, can you just run through how you go about doing that test? I know it's pretty simple, but essentially where are you hooking up the leads? I guess that's the big question.
Well, the easiest way to do this is just to bundle the lead wires that come out of the sensor and hook one of the leads on the meter to that and touch the other one to the probe sheath. And because it's a high-level resistance check, you want to make sure that it's, ideally you want to do it on an ESD table so that you don't have any stray voltage, static, whatever flying around, and don't be touching the part. We even do some high-level measurements here where somebody walking by with a real fuzzy jacket that's got some static in it will throw off the reading. It's that sensitive. So, but with this, that really wouldn't be an issue at this level. But so again, ice bath check. Ice bath is real easy to make up, and you can plug the sensors in there, go ahead and measure them with a high accuracy ohm meter or other device you may have, and they should repeat within, at least within the initial interchangeability numbers. And if it's outside of those limits, really maybe should consider replacing the probe, because it means something has happened to that sensing element, and it's a bit questionable. The last thing I want to talk about here today was some of the other error sources that come into play when we're doing any kind of an error budget calculation. So if we look at typical application, and here we have one that's got an immersion length that's actually shorter than what is ideal. It's 2.5 inches of immersion, and we're using 100 ohm typical PRT. It's a grade B sensor and a transmitter, and the objective was to control to something better than 0.5 degrees C. So if we look at taking these parts just off the shelf, plug them in there, we've got our interchangeability at the temperature of 121 degrees C, which is already over half a degree C. Just picking that class B sensor. We've got some insulation resistance error, and on down the line. And you'll get these from the manufacturer spec. Some of these are application specific. Others are kind of your best guess as to what it might be, especially down here with stem conduction. And this was a number that was just kind of guesstimated from the graph we looked at earlier. Again, almost half a degree C. So you can already see that we're going to calculate a number here that's not going to be better than 0.5 degrees C. In addition to those numbers for the RTD, we have the transmitter, and you can pull these off the manufacturer spec, include that in your calculation. If we take all these errors and combine them using root sum square, we end up about 0.713. And if we apply a coverage factor, so for 95% confidence level, wow, we're almost at 1.5 degrees. That's a long way from where we want to be. And this is just taking standard components off the shelf, hook them up, plug them into the process, and away you go. So you can see that just doesn't work for getting that something better than half a degree C. We really need to go through and improve each one of these things, not only with the sensor, but also with the installation. So if we were to use a grade A PRT, well, that gets us part of the way there. But the best thing yet is to go ahead and match the sensor to the transmitter, or if you can match it to whatever control equipment you have in that measurement loop, that works also. And we can get rid of a whole bunch of the interchangeability numbers with the probe. We take that grade B sensor, calibrate it. We end up with about 0.08 degrees C. The installation errors, whether it's due to stem conduction, time response, look at eliminating those, taking that sensor, putting it into an elbow thermal well or into a T fitting. We can drop that installation error down to near zero. Plug all those numbers back into our root thumb square coverage factor, and now we're at 0.39 degrees C. And that's probably a very realistic number that you can get with off-the-shelf industrial style parts. So there's a lot that goes into this, and looking at each one of those error sources, and it seems like every application is a little bit different. Everybody's got their own situation that arises. I was talking to somebody a couple days ago. They had a incubator where they were seeing about between a 3 to 5 degrees C error, and it was reading warmer than it should. And right away I think, okay, this is an installation problem. An RTD cannot fail that badly, usually without failing completely or being erratic. And by looking at their installation, they determined that someone had actually strapped the probe to another device within the incubator, and that device actually would heat up a little bit as it was running, and the sensor was detecting that temperature. So the fix was very simple, was just to mount the sensor in a different location within that particular incubator. Again, installation errors, usually the biggest problem and need the most time and effort put into making sure that the piping design is done such that the available sensor designs are going to work within that to give you the best accuracy possible. And one of the last things I wanted to mention here, if anybody's interested in learning more about uncertainty of measurement, there's a real good document written by Ms. Stephanie Bell at the National Physical Laboratory. It's written in a very nice, understandable manner. So you can just Google that, and you'll come to a link to download it. So just to wrap this up today, it looks like we're kind of running short of time, and we've got a few questions to answer. Getting beyond that plus or minus 0.5 degrees C accuracy for a measurement, you need to know a lot more than just the interchangeability of the sensor. You're not going to get there by just picking Class A or Class B sensor and plugging it in. There's a lot of other error sources that are associated with the PRT themselves. The two standards that govern, they're not completely comprehensive, and they're not real stringent. So you really need to lean on the manufacturer to look at and provide performance specifications for the RTD and the transmitter, or whatever other component you have in that measurement loop. Need to know some specific details about the application and the piping design, and again, look to the manufacturer for help with those sensor error sources. And I guess with that, we can look at a few more questions here.
Yep, absolutely. If you do have questions, go ahead and type them into the chat box, and we'll get to them. We do have several questions, but if you've got more, please type them in, and we'll get to them. So to start with, a question: what do you mean by matching? And I think referring to transmitter matching. Can you talk a little bit more about exactly what that means?
Yeah, when we match a transmitter to an RTD, what we'll do is characterize the resistance of that RTD over several temperatures. So typically for a lot of biopharm applications where you might be doing 121C, probably do a calibration at 0, 100, and 200 degrees C, and then generate the calibration coefficients. And we can take those coefficients and enter those into the software in the transmitter so that it's generating an R versus T curve, and the transmitter then, when it sees that resistance, it's going to output a known current. And when we do that calibration, we're eliminating the interchangeability number for that probe by characterizing the exact resistance that that probe produces at a given temperature. And that's what with the smart transmitters, you can plug that information into them. If it's an analog transmitter that just has zero and span potentiometers on it, for example, we may measure the resistance of the probe at the 0 point for that transmitter at whatever temperature you choose as the 0, and then at the maximum temperature. Or you could also maybe do a midpoint too if you wanted to kind of tweak it in if you only are interested in one temperature. But you're depending then on the linearity, or the actually most transmitters are not linear anymore, so they'll have some kind of a temperature curve plugged into their brains, but it'll be fixed. So you're going to be on at the 0 and the span number, but in between it might be off a little bit. So that's not the best way, but it's a lot better than just taking a transmitter and a probe and just hooking them together without doing anything, just using nominal numbers. So I turn that back to Jeff.
Okay. Yeah, another question related to the same thing. Just some terminology. Could you just define 0 and span? I think that was another question on the transmitter.
Oh, okay. Yeah, on the if you look at just an analog transmitter, for example, you'd set up your 0 point, which should be outputting 4 milliamps, and the span is the maximum that it's going to measure with a 20 milliamp output. So that's what we're talking about when we say 0 in span for a transmitter.
Okay, there's another question just looking from Tracy, wondering what's the most robust probe for measuring liquid nitrogen? So minus 195 with a thermometer. So maybe talk a little bit about what we'd be looking at there.
Yeah, one of the biggest concerns with down below 0 degrees C is how do you handle the frost that forms on the probe? If it's in a like a storage freezer, you're always going to have frost buildup, or when it comes time to calibrate it, you're pulling it out and setting it on a bench, and it's going to form frost, and it's going to melt and sit there in a puddle of water until everything dries out. So we really got to be careful about moisture getting inside the probe during the calibration, or just a portion of not being used. And so the best probes are going to be completely sealed against moisture. It'll have a some kind of specification that says that it's fully immersible. That's the thing to look for. The next thing would be performance at the low temperatures. And when we get down that cold, the cable insulation can be a bit of a problem. We're pretty limited in the number of materials that can have any kind of bending or anything done to them at that temperature. Those materials tend to crack, so you'd have to be fairly careful there with like repositioning the probe as it's in the freezer that cold. And performance, I guess you'd really want to quiz the manufacturer on the style of sensing element that's being used. There's a couple different ones that if it's a thin film sensor, for example, versus maybe a coil wound, and you maybe don't need to know that specifically, but look at the performance numbers for those colder temperatures to make sure that you're getting what you need for accuracy at those low temperatures.
Okay, we've got another question from Thomas. Could you describe a tip-sensitive sensor? Aren't they all tip-sensitive?
You know, they're not all, I guess what, it's just kind of the magnitude of what we mean by tip. Most RTDs will have about a 1-inch sensitive length right at the very tip of the sensor. And when we say that a sensor is tip sensitive, it's relative to what that 1 inch is versus maybe having just a 1/4 inch or maybe 1/8 of an inch of that tip as only being sensitive, where there's a real short, very small sensor might be potted into a small copper block at the tip of a stainless probe. And that's really what we're referring to as tip sensitive. It's not so much along the side of that probe, but just right at the very end of it is where most of the heat transfer is taking place.
Okay, we've got a question here about when the transmitter head is threaded onto, say, like a sanitary body of a sensor, does the potting compound serve the purpose of insulating the sensor from the ambient effects on the transmitter body? Say a cold room and a steam measuring RTD with a transmitter body.
Yeah, that's a good question. The conduction will happen along the the connection head and all the metal parts that run down into the process and surround the sensor, but it also can come down the lead wires for the sensor. So in addition to having like a small diameter sensor, maybe real thin wall materials to minimize that heat conduction, smaller diameter wires internally can be used to minimize any kind of conduction path down to that sensing element. And the heat transfer paste helps to helps to maximize the transfer between the your process fluid and the thermal element and the sensor inside of that. And then internally in the sensor, the potting materials, they can make a little bit of a difference. If you were to just put a sensor inside of a tube and just leave air in there, for example, versus filling it with epoxy or filling it with a heat transfer paste or maybe some kind of a Teflon shrink tube over the sensor or silicone rubber, those all have a little bit different characteristics, and they're going to have some effect on that conduction air from the outside portions of the transmitter head down to the sensing element. But really the ones that are immune to that is the lead wires, because we've got to have lead wires running down to that sensor, so that path is always there.
Hey, a couple more questions here. Robert asks, on the insulation resistance test photo, how is the test at 50 VDC possible just using a simple DMM?
Well, that was just a little photo convenience there. The actual meter probably wouldn't look like that. I had chose that one just because a lot of people recognize that as a DMM, and the actual little box that's used, at least one that we use, looks a lot different than what that is, and it really depends on the level that you want to do. Like if you're measuring up in the teraohm range, you're going to use something a little bit different, and if it's a megaohm range, you got another device that does that. So, but it's a good question, and you caught me, and a
little poetic license, huh?
You win the prize for today.
Another question from Christopher: are there significantly different considerations when measuring temperature in ambient air, e.g. refrigerator, incubator, compared to fluid in a pipe?
With air temperature in a freezer, refrigerator, incubator kind of thing, what we see there a lot is a concern with the probe responding too quickly. And so there are ways to slow that down so that, if you open the door of the freezer, incubator, you can put stuff in or take it out without an alarm going off. So that's a consideration there. There are some solutions for that. And you know, if you're have the opposite problem where you need to have that probe respond more quickly, you know, they are going to measuring in air. Typical RTD is going to be about, you know, maybe 10 times slower than it is in a fluid. And you're also going to see a difference in the immersion requirements. And I had a situation once where someone was trying to monitor room air temperature, and so they put some 5.5-inch probes sticking down from the ceiling, and they had a transmitter head above the ceiling, and I guess it was just some kind of a suspended ceiling, wasn't insulated or anything. And of course, up above the suspended ceiling, you know, it was summertime. The temperatures got up to about 90, and in the room, they were trying to control it to maybe 20 degrees C. Seeing a big conduction error with that, just even at 5.5 inches, it wasn't working correctly. And so the solution there was to have about a 2-foot-long RTD that would stick down through the ceiling and then take a 90-degree bend right away to go parallel to the ceiling and have it, you know, about 6 inches away from the ceiling. So it came down 6 inches and then extended out, and that was enough immersion to eliminate that conduction problem that they were seeing.
Just wanted to remind everyone we are at our time. It's been an hour, but anybody who wants to hang on, we've got a couple more questions. We'll go ahead and answer them. For those that can hang with us, we appreciate it. For those that can't, we want to thank you very much for attending the session, and wanted to remind you that we do have future RTDology sessions. The next one is I believe RTDs versus thermocouples coming up in February, and then we also have RTD accuracy again and some temperature basics. You can see what's coming up the next few months. So we want to encourage you to join us for those. And with that, thank you very much. For those that can hang on, we've got a couple more questions we'll go ahead and answer. So in regard to the ambient, Joseph made a comment that potentially silicone oil in a bottle, that being food grade, might work for incubators. So in other words, maybe using a direct immersion into a bottle of silicone to, you know, measure ambient rather than having the sensor directly into air.
Yeah. Yeah, the concern I've seen there is, you know, they don't want to introduce, again, any kind of stuff inside of their incubator or freezer, refrigerator, whatever, in case it gets spilled. It can be a problem cleaning it up. So there are some other solutions for slowing that response time down so that you don't alarm when you do open those environmental chambers. So, you know, one other thing I wanted to mention here before we move on to the next one, you know, if you have any other questions, there is a temperature measurement group on LinkedIn, and so we've got people there from all over the world. You know, if you have another question, you can throw it on there, and get a lot of good responses that way too.
The question from Dan. Bill had outlined a list of questions to ask when in the selection process. Do you have a form or template that includes these questions, or is it located on our site? Well, I can tell you we'll get a full copy of the presentation, so it will be in there. I'm not sure if we have. I think there may be a form around someplace. We will take a look, and if we have one, we will send it along. If we don't, we certainly could create one. I don't believe it's on our site individually, but it will be with the presentation notes that we send you.
Yeah, there's actually a good portion of that in the selection and application RTDology session we did a while back. And
okay.
The slides there are on the website, so you could download that there and get that. So,
right. So that would be under burnsengineering.com under the RTDology tab. You'd be able to find those session notes.
Right. Yep.
Okay. I think that is about it. So again, want to thank everyone for attending and everybody for their questions. If you do have other questions or challenges, by all means, send us an email or give us a call, and we'll be more than happy to talk about your specific application. In the meantime, we hope to see you again at the next RTDology, and please enjoy your afternoon. We'll see you later.
Thanks, everybody. Bye now.